This lecture is on single slit diffraction, and we first take a look at Huygens principle. And in order to understand single slit diffraction, we have to realize that every point on a wavefront acts as a source of tiny wavelets that move forward with the same speed as the wave. The wavefront at a later instant is the surface that is tangent to the wavelets. So you get these little tiny wavelets all interfering constructively and destructively together. So here are two pictures of single slit diffraction. Here you'll notice that the width of the slit W, the width of that single slit, is pretty large compared to the wavelength, which is pretty small. So you get much less diffraction. Not a lot of diffraction occurs on those edges. Here you have a single slit that's it causes much more diffraction. It's squeezed in. And you'll notice right in this area there's a central maximum. And this squeezing in of the wave causes the wave to diffract out wider. So as your width of your slit decreases, the size of the diffraction, or the amount of the diffraction, gets larger. Now on the left-hand side, if you have a very wide slit, you don't get very much diffraction. But on the right-hand side, it shows if you make the slit much smaller and you start squeezing the light, you'll get areas of constructive and destructive interference. And you'll notice that the central maximum for the single slit diffraction grating is much wider than you would see for a double slit or a multi-slit diffraction grating. So here we have an example of a wave coming into a single slit diffraction grating. And according to Huygens principle, areas 1, 2, 3, 4, and 5 act as little wavelets. And right here you get this midpoint of central bright fringe. This is where the central maximum is. It's very wide. And now what you get is your first dark fringe area. These wavelets all come together and interfere destructively at this point. The variables we use in a single slit diffraction grating are W is the width of that single slit, L is the length between the slit and the screen. That's the same as we did for a double slit diffraction grating. This is a little different over here though. The Y value, this height, goes to the first dark fringe where M equals 1. So you have to be careful. This single slit diffraction grating is different than the double slit in the sense that M equals 1 at the first dark fringe, not the first bright fringe. M equals 1 where destructive interference is occurring. So our equation is a very similar equation, sine theta equals M wavelength over W. And this again is for the dark fringe for a single slit diffraction grating, M equals 1, 2, 3, etc. And we have to realize this equation is for the dark fringes. So here's an example of a single slit diffraction grating. We have this light coming in. It diffracts. According to Huygens principle, you get these wavelets that start acting constructively and destructively. And so you'll see the central maximum that's very wide compared to the first order or the second order. You'll also see this graph that shows the intensity of the light is very high in the center and dies out as you go outwards. If you change the wavelength of the light, of course if you go to red, you see that the waves spread out because of the longer wavelength, and then when you go to violet, they come in close together because of the shorter wavelengths. So here in this case we have our slit width here is W, our length L is the distance from the diffraction grating to the screen over here. Our Y value is from the central maximum up to the middle of the first order dark fringe. And our wavelength, of course, is the wavelength of the light. So if we look at an example here, we see that we have a problem that says light passes through a slit and shines on a flat screen that is located 0.4 meters away. The width of the slit is 4 times 10 to the negative 6 meters. The distance between the middle of the central bright fringe and the first dark fringe is Y. Determine the width 2y of the central bright fringe when the wavelength of light in the vacuum is 690 nanometers, which is red light. Now they're saying the width of the central bright fringe has a width of 2y. which makes sense because from the center to the edge where the dark fringe is 1y. So we're finding the 2y value. So pause the video and see if you can find this. So we start off by finding the angle. Theta equals inverse sine of y over w, and that gives us about 9.9 or 10 degrees. Then you use then you plug in that angle to tan theta equals y over L. Solving for y, we end up with 0.07 meters, and then you want to double that to get the width of that central bright fringe to get 0.14 meters.